So we're happy to have Joerg Teschner from Hamburg, who will talk about Liouville theory and quantization of Hitchin.
Yeah. So trying to say that Liouville can do more than just that. So
can you speak up?
Huh? Louder?
Louder.
Yeah. It will come. Okay. So say well. Basically, I want to present a kind of big picture where sort of aspects are getting more clear, some aspects are still slightly mysterious to me, and so on. And well, what I'm not going to talk about is what this has motivated some more work, some more thoughts about these connections, which is these recent developments in gauge theory that we have heard of. Well, several aspects. So, okay, basically, well, a major source of inspiration is in particular the work of Nikita and Samson, which indicates that in a way gauge theory has this the power to, well, one starts in 4 dimensions, so one has some classical integral system associated with gauge theory. As Andy has nicely explained, so here it would be the Hitchin system. And okay, then gauge theory has various very clever ways to introduce deformations thereof, going under the name of omega backgrounds or epsilon deformations. So in a way, okay, they deform the story. The claim is that, well, the claim of Nikita and Samson is that turning on one parameter does the job to quantize the classical integral system. This is this arrow. I will say little about this, but it will not be the main focus. On the other hand, well, there are these 2 parameters, and sort of what I tried to meditate a little bit about was what the role of the 2 parameters is and how they could fit in one unified picture. So here's this arrow I want mainly to talk about. Maybe you can deform the Hitchin to what I call isomonodromic deformations. It is also, of course, closely connected to several things we've heard of. Moduli space of local systems, and so on and so forth. I just put isomonodromic deformations because in a sense this is the integral structure of this way of looking at Hitchin moduli space, as I will try to explain a little more. And then, okay, this arrow here is basically, well, for those who know in a nutshell, it's the deformation of the space of local systems, to be more precise, a real slice thereof, because often if you have an arbitrary integral system, okay, it's a complexification of something real, something more physical, and so this is a real slice, the phase space, and so real slices in this space, I claim, if I quantize the Liouville theory, part of the story is kind of known in the sense of that this is precisely what corresponds to quantization of tabular space. However, there's some interesting extension of the picture, and furthermore, what I also tried to understand was a little more, was the relation to the recent work of Nikita and Hitchin, which basically indicate, well, goes some way understanding these relations in indicating that on the one hand, what we're looking for, what gauge theory does in the quantization, well, carries an action of a quantized algebra of functions here on the space of local systems. And second, it has a representation which comes from something like quantization of space of pairs. This is maybe slightly mysterious still, and well, I will not give the full answer, but I will give, well, maybe we can discuss later what I have told you and what I should have told you. Okay, so let's start with some reminders about the basic. Basically, I start here on the top of my diamond. Maybe I should put this diamond here for reference. Classical Hitchin, Hitchin, isomonodromic, and here Liouville. Or, okay, Liouville, as we know, is another incarnation as with the Witten model, but the way it gets incarnated because in the Witten model is not even trivial. Yes. Okay, so Hitchin's integrable system, the phase space that we're looking at, phase space we want to quantize, is the moduli space of Higgs pairs. So we have a holomorphic SU2 bundle on the Riemann surface C. Well, we can think of it as coming from a vector bundle, a smooth vector bundle with a connection. We're taking 0,1 part in order to define the holomorphic structure of it, as usual. So it's sometimes useful to use these data for describing it. And the so-called Higgs field, which is a one form, which used in the joint, and transforms under the gauge transformation as indicated here by just conjugation. Now, so this is considered up to complex gauge transformation, and then there's a moduli space of dimension 6g minus 6 plus 2n. So it's a finite dimensional space ultimately. We associate to a Higgs pair this quadratic differential, the trace of eta squared. It's a quadratic differential. There's a finite dimensional space of quadratic differentials. We can expand this guy with respect to the basis. So what this defines is a collection of functions on this Hitchin moduli space. And these functions, which is we have just half as many as the space has dimensions, these will be called the Hitchin Hamiltonians.
I have a nice question. In anticipating connection to Liouville, wouldn't it be more natural to take real slice of this as a phase space?
I do not yet take a real slice, and as Nikita can probably explain much better than me, there's a lot of interesting subtleties concerning how to precisely go to the real slice in quantum theory. I will not really go into this issue here, but we can maybe discuss it later. But indeed, I mean, I want to be more precise about real slice, basically here, and because this is the main quantization error I want to explain, but spare me to discuss this here just for the sake of
Yeah, my question is more basic. Okay. I'm not questioning how we choose the real slice. I'm familiar with those problems. The question is about dimensions, because here you're roughly speaking working with complexification that's twice as big.
Yes.
So the question is why? It's a more elementary question.
The question is why
there's no real
of course in examples. We're going to do an example like we've done. So there you can formulate it in terms of real variables only. You're writing down some Hamiltonian depending on moduli of the Riemann surface. So then you have to impose some conditions on moduli of the Riemann surface also in order to make relative properties simple, and then you have the phase space variables, which are something which appears in the differential operators and so on. These you can assume to be real, but you can of course also complexify because everything is algebraic. So, and it is mathematically in many respects very useful and instructive to study firstly.
Joerg, I think that the fair answer actually is that the system is given like that. It's given as algebraic complex integrable system. Right. And it's not given any other way in the beginning. So you have to find P's and the Q's which are... That's the way it came.
Yes.
The complaints to Hitchin.
I completely agree, and then you have sort of the story of the reality conditions, you postpone it a little bit. Right. That's the attitude. Now, for writing formulae, I will mostly reduce it to the simplest example, because otherwise it would take too much time. So that is genus 0, where the special case of the Hitchin system is the Godot model. So to see how to describe it, we can use a gauge where A01 is just 0, so everything is basically in the Higgs field. We have n punctures or marked points, so the data of the phase space, the variables, are just the residues of the Higgs field at these marked points. That's all we need to study. And then if we form our Hitchin Hamiltonians, what we find is an expression of this form. The deltas are just Casimirs, which we set to Higgs numbers. So from now on, they're just these numbers. The interesting part is here. So we're finding some quadratic expressions in terms of our basic phase space variables, the J, A, R, And these are well-known expressions. This is what appears in logic of equations and so on. Okay, for the moment everything is classical. We need to define the Poisson bracket or symplectic structure. So the abstract way of writing it is like this. This defines a holomorphic symplectic form on our phase space called omega I. And it is such, it turns out, that's the little theorem, that the Hitchin Hamiltonians commute with respect to the Poisson structure coming from the symplectic form, and this is the basic statement of integrability of the Hitchin system.
So why did you put an R there?
What?
So the R there.
Oh, the R, that is the same as yours. Because, okay, we will use it at some point. Okay, well, there's a rather universal scheme for addressing integrable models, which goes under the name of separation of variables, and in a way you can view it as sort of half step towards the solution. Namely, it's a useful set of variables which partly decouples the dynamics, but there's something much of it that remains. So here we can do it very concretely. These were the J's were our original phase space variables. Now we do a change of variables by just finding the zeros of this J plus, so which is this off-diagonal element here of the Higgs field. So we're going to the zeros of J plus. Okay, if we count here and if we say take care of the overall invariance, we're having n minus 2 of them. So these are now our new variables for the phase space. We define so this is half as many as the dimension of the phase space. We define another half as many dimensional set of variables by evaluating the J0, is this component here, at the zeros.
What is mu I?
Mu I, oh yeah, this is, sorry, I was copy and paste, so mu I is JR plus. So mu I is JI plus. And okay, the key observation is, which was made by Stony, that these variables again form, well, not again, for the first time here we have canonical conjugate variables. So that is already very useful, and in particular it will give us a quick entry into the quantization. Well, important note is that when we fix the values of the Hamiltonians, so we have fixed values of the integrals of motion, then the pairs Kr, Yr are restricted to a Liouville curve. Of course, fixing Hamiltonian defines a curve in the phase space. And this is the famous spectral curve, so which is defined as the pairs of complex variables k and y, which satisfy the equation that k squared is q of y. What it defines is a double cover of the Riemann sphere with n-marked points in our case. Okay, well, now we can sort of the fun part. We just quantize. We have canonical conjugate variables. We just quantize. So we make these operators with these commutation relations. So we introduce here some, well, h bar in the suggested form because I had put here, well, epsilons, not completely random manner. So this epsilon is now, the epsilon is just one of those. Okay, so what does it yield? Here the Kr is the canonical conjugate to Yr. So this now becomes represented, or it's natural to represent it as the differential operator. Here I forgot to put a square, so it should be the second derivative, of course. So quantizing this relation, which is the defining equation of the spectral curve, yields Uka. We have heard of Ukas before. So this is a nice way how to very quickly arrive at the connection between the eigenvalue problem for the Godin model and O pairs. And okay, so here if we would expand these, the Q, well, the same expansion as what we've seen before. Here, what appears as accessory parameters are nothing, but so in Leon's talk it was nicely appearing. So these are now here the values of the Hitchin Hamiltonians in our case. So that's sort of a nice, standard lore by now in a way that the quantization of the spectral curve, this gives what is often called the Baxter equation. In our case, it's just the O pair. Well, okay, of course, this now, in the quantum theory, we cannot just set identically to 0, so we need to impose it on eigenfunctions. So on eigenfunctions have to satisfy this equation. Well,
is there another misprint?
Square.
Another, yeah, you see, I'm sorry, I was. it is copy and paste and so on. Yeah. Sorry.
There's this more serious thing that if you actually compute, don't compute the classical theory and types of compute the quantum theory to begin with, the case which you get will be not just derivatives, it will be conjugating derivatives. The conjugation is important because that defines the measure for your set function.
I know, yes. Of course, there is an issue that I shall skip. It depends on how precisely you define the representation and
where does psi live? Where does psi live?
Where does psi live? Anyway, claim was clearing that there exists a representation where I do have these relations, where I do realize as these operators, and where I do have ultimately reduced the problem to find the eigenvectors of the Hamiltonians to finding solutions of this decoupled set of equations where we have only appearing one variable yr at a time, which I can therefore solve in a factorized form. So the study of the spectrum reduces to the study of the set of solutions of this, well, in our case, second-order differential equation. And, well, the whole subtlety, the whole fun of the game here now is to find precisely the conditions, the boundary conditions, analytic conditions, which describe the Fourier spectrum. And this may change precisely by, for example, what kind of real slice I've taken, what kind of scalar product I've imposed, and so on. I shall skip this. This is just for Nikita and Samson very quickly. Okay, in our case, we can give a very precise answer for what Young's potential is going to be. We can discuss where this comes from in the discussion section, but that is sort of one of the takeouts that I just, okay, I want to say. The formula is there. Let me describe it. We can define functions HR, which depend on the z's, which are just the positions of the marked points, and L. What is L? So for each pair, I have the monodromy representation. I can pick a maximal set of non-intersecting loops, or what defines a Planck composition. I can evaluate the trace of the monodromy around these non-intersecting loops. This defines three parameters LR. Now I can do, via Riemann-Hilbert, the inverse problem. I can try to find the H's such that for given L's, I'm reproducing this monodromy, these conditions. Okay, so this is the rather implicit, I admit, definition of functions HR of L and Z. So L is the tuple, that is the tuple of corresponding variables.
Where was here the choice of real slice? At what point?
No real slice. Yes. No. You see, that is, I think this is your point. That the Young's function is something which is analytic in its variables.
Right, but then.
And the real slice then enters in how you define from Young's potential quantization conditions.
Okay.
That is, I think you explained it very nicely.
That will exist without the choice of real
Right.
Yeah.
Okay, I will. Okay.
So, okay, so this is the definition of HR as a function of L's and Z's. And now I claim, and this is of course the sort of slightly non-trivial fun part of the story, that these H's come from a potential. No surprise maybe to you, the potential is semi-classical Liouville conformal block, and this is what one could have guessed if one just observes that, okay, if one combines AGTs or with what Nikita and Samson have done, this is precisely the prediction that you would find, that the semi-classical Liouville conformal blocks have the potential, the Young's potential. Well, but okay, if we have time, I can just from the semi-classical limit of Liouville theory argue that the integrability condition for this equation is satisfied. Okay, so that's a side remark in a sense. Now let's return to the main theme. First of all, now basically we want to go that way down. We want to deform from classical Hitchin, or if you wish, from the Hitchin modular space in complex structure I, I to the representation in terms of flat connections, which is Hitchin moduli space in complex structure. J also, of course. But okay, here's the better statement. So, first of all, there's a theorem of Hitchin that for any stable Higgs pair, that's what it's stated, there exists a family of flat connections which you can write in this form. Okay, so I wrote it in terms of, well, the data which made the original Higgs pair, which is theta or Higgs field and A01. And basically the statement is that you can supplement it by some suitable A10 in such a way that this connection is flat. That is theorem what we need to solve a nonlinear partial differential equation. We're introducing convenient parameters here, basically following, well, Andy, Davide, and Greg, so it's basically the same way they do it, where then the zeta is the hyperscalar parameter. So there exists a family of complex structures now in terms of this picture of the Hitchin moduli space, which are characterized by the property that holomorphic functions of the connection, like for example traces of monodromies, that they are holomorphic. Describes the complex structure, and there's associated a family of holomorphic symplectic forms which can be defined like that. That is exactly what, for example, Sasha's talk is the structure he was using. Now, flat connections, modulo gauge transformations can be characterized just by the monodromy representation, so I can think of the Hitchin moduli space as just being the space of representation of the surface group, the fundamental group of the surface into TSL2C. That is of the convenience if I just think of this being the fixed data describing this space. Now, next step. From flat connections to local systems, well, we want a holomorphic description of the space. We can use del bar plus A01, or A01 is the thing here combined out of the connection and the Higgs field, to define a new holomorphic structure called A zeta on the underlying bundle. And then the flat connection is represented in terms of, well, just the A10 part, or it's a little more convenient here, we just modify it slightly by introducing this fancy-looking epsilon connection, which is nothing locally but a holomorphic matrix differential operator of the form del plus m of y, where, okay, we introduce the parameter epsilon here, and the parameter epsilon is related to the previous ones in this way. Well, this means this connection, if I just have this thing as a convenient gadget, it does not exactly transform as a connection, but I have the epsilon here in front of this homogeneous term. It's in principle not a big deal, but it's, well, the nice thing is that it gives a nice holomorphic way to think about this parameter zeta, the hyperscalar parameter. Okay, now, canonically, there comes some integral structure with that, which is, in going to the holomorphic description, we had to use the complex structure of the underlying surface. So far, we were not using it at all. The description in terms of flat connections is logical and is not using this at all. So, well, if I change now the complex structure, it would mean I have to change the matrices accordingly. What this means is, okay, I can keep fixed, and that's natural, just the monodromy representation. So, a very complex structure with fixed monodromy representation. I'm getting a resulting deformation of the matrices m of y from this construction, basically. So these are isomonodromic deformations. One can prove, of course, there's a little work to do, that the resulting flows commute with one another, so that is some integral structure.
But when you talk about the monodromy representation, that's the monodromy representation of an actual connection, right? Not an epsilon connection.
Yes. Okay.
You fix the complex flat connection, and then what we do is we change the complex structure, and we change different. So we change the underlying holomorphic bundle, and we change the.
No, the underlying holomorphic bundle I keep fixed, and I just change the complex structure, which was defining the decomposition in 0110 part, and so therefore I will end up with a changed representative m of y locally for my connection.
M of y is just currently a sub zeta 1,0?
Curly A sub theta 1 comma 0. Yes.
Up to some
Yes.
yeah.
Yeah, up to.
So you change complex structure on C. You keep the full connection you keep fixed.
Yes.
So you change complex structure.
I changed just the way I described the flat connection in terms of holomorphic data, in terms of these holomorphic matrix functions M of Y, but I keep basically some underlying flat connection as data fixed.
But what holomorphic bundle? Curly E sub A.
I can keep it fixed if I want.
I don't see how.
That's my question.
Well, the way to think about it is you can vary zeta in R, keeping R zeta fixed. Okay.
A sub A1, 0 mixes up with A0, 1 when you change complex structure.
So now theta bar mixes, everything mixes.
We are changing complex structure on C or on the bundle?
No, but I'm asking that it seems that changing the complex structure on C also changes the
Sure, but it becomes very complicated. Usually the curve stays, you vary the bundle. The
That's
holomorphic
easy,
structure
yeah.
in the bundle. Yeah.
What if you're deforming?
If you form the curve, then it becomes very...
Let's forget maybe, I mean, first
So what
we forget about epsilon to begin with. We don't need it for this consideration. We just have ordinary connection and epsilon.
Okay, but what are you deforming when you talked about isomonotopic?
Well, I'm
We know what you keep fixed. That's not connection. That's why
Yeah.
it's asymptotic. What do you deform?
You move the punctures, you keep
well,
the curve.
moving
you
the
move
punctures, and
singular
okay, it will maybe become clear in the example in a moment. But
you move
of
singular
course,
points,
if I
the curve,
change the complex structure, the point is that here in this splitting, I mean, I vary the splitting. So I change the complex structure, so I have to, now with a change complex structure, I do the game of decomposing in 1, 0, 0, 1 part. Yeah, of course you're right, you have to, yes, sorry, I was saying something stupid, but of course then you also are varying the bundle underlying.
Okay.
Sorry.
There is some connection. So
Yeah, there's a connection describing this transport. Okay, well, let's do it concretely. Of course, the literature.
To identify this with more specific unitary flat connections, and we could also keep unitary flat connections. So that would tell you how to transport the multiple. I don't know what we're doing, so that's why I'm asking.
Fixing the monodromies of the complexified connection.
Right.
That completely
enough.
describes
That's not enough because then if we want to have a flow in the space of local systems, we also need to identify holomorphic bundles, underlying holomorphic bundles. One way to do it is via unitary flat connections.
Yeah, okay. The discussion here is
In
more
genus 0, this problem doesn't arise because the
I
holomorphic bundles
agree.
are typically triggered.
Yeah, I agree. The discussion here is not complete. Let's go to some example and refer to literature for full story. I mean, there's a paper of Simpson, for example, which, in very abstract terms, which I do not completely understand, explains how this works and so on. It is in a very explicit way, for example, discussed by Kricheva in a paper. So, maybe this is from the first level of understanding. Good enough? So, okay, well now if we do genus 0, what we get is something very familiar and classic, the Schlesinger system. This should be d by dy here, so basically it looks like, well, the Higgs field we had in Redon, except that we have now the derivative, and somehow the way to think about it is, okay, I should have also put the epsilon here, now I'm setting it to 1, but if I play with the epsilon, of course, I can drop this term and I'm back to Redon. I'm going from ordinary connections, the epsilon just does the job to interpolate between ordinary connections and Higgs fields. We're again fixing conjugacy classes of the matrices, and now these famous nonlinear equations ensure that if I vary the positions of these marked points, the R, which now represent the choice of complex structure, these equations ensure that the monodromy of this connection stays constant under these variations. Okay, so what we're dealing with is a non-autonomous integrable system, which means that the times that we have here, the deformation times, well, appear explicitly in the Hamiltonians. I don't write the Hamiltonians, but okay, you have the ZR minus the S contained in the Hamiltonian. Basically, it's the same Hamiltonian as before. And furthermore, okay, we have a natural set of conserved quantities now, which are the monodromy data by definition. So I think a useful way to think about this is we have on the one hand local observables, which are the Hamiltonians, just for convenient handy terminology, and we have non-local observables, which are the monodromy data, which here are representing the conserved quantities, while local observables are manifestly and explicitly time-dependent. Yeah, O+ again. So, from local systems to O+, and here this again basically is independent of these. So by means of polymorphic gauge transformations, I can always get rid here of the diagonal elements. I'm left here basically with two matrix elements. I can also set this, I mean, what I'm aiming for is a description in terms of second-order differential operators, of course. But the obstacle is that this is y-dependent in general. I have to set it to 1 somehow. And in general, I cannot set it to 1 because, well, the gauge transformation which would do the job is singular. But anyway, let's do it nevertheless. So we are conjugating here by square root of beta of y, which is clearly singular at the zeros of beta. But okay, it's not too bad if we think about it. So we are doing this conjugation and we're finding something of the form where I have put here 1 and here I have basically 1 over beta. So the previously perfectly polymorphic connection M now has additional singularities. These are called apparent singularities, and these singularities occur exactly at the zeros of the beta. But as they are gauge artifacts, they do not change the monodromy. This is why they're called, I mean, what is part of what justifies the name apparent singularities. In the form where I've set it to 1, it's of course standard to transform the differential equation, well, del y minus m prime to a second order differential equation, which again is of the form well, let me really stress here that, but it comes back, that we're doing something analogous to as before, and we're doing basically separation of variables now for the Schlesinger system, and we were trying to parameterize the phase space in terms of the zeros of beta. Sorry, it's very analogous, it's just sort of the deformation of the story before.
M prime is where you gauge y to 1, beta to 1.
M prime is the one where beta is set to 1. Yes. Okay, so the resulting T has this form, so this we have seen before. Now this new aspect coming from these apparent singularities is here. It should be minus, by the way. So, okay, we have these singularities, and we have also here parameters describing the residues of these singularities. Now, it is something rather remarkable, and but okay, let me not go into the details too much yet. The condition that this differential operator has no monodromy at these points can be formulated just as an algebraic equation for the coefficients. Namely, we're taking the expansion of T near each of these apparent singularities. So we have T0i, T1i, T2i, and so on. These are the and the claim is that this constraint is sufficient. I mean, necessarily it's sufficient to ensure that this differential operator has no monodromy around the apparent singularities.
Large delta is the same as small.
Large delta? Oh, yes, yes, sorry, this is right. It should be small delta, later having large delta, which are conformal dimensions, of course, but there's a rescaling by h bar involved and so on. Okay, so these are these constraints written out explicitly. We see these are linear equations for the ages. So they can be solved. I mean, there are just linear equations for the ages. They can be solved to express a certain number of the ages in terms of the remaining variables, which are kappa and w. And in the maximal case, I mean, here I take the freedom to vary this number, but the original Schlesinger case would correspond to d equals n minus 3. Then I have enough equations to get all the Hamiltonians in terms of kappa and w. And the expression clearly is quadratic in kappa, so it's really Hamiltonian because kappas are my momenta now. And so yeah, I have some Hamiltonians which depend quadratically on kappas and in a more complicated rational way on w's.
So, sorry, I maybe missed something. It introduces some good coordinates.
Yeah, these are like Lex-Bienning's coordinates, except now we're doing the non-autonomous case. It's exactly, I mean, this is one of the points I'm trying to stress. So very universal ideas here. So, okay, so this equation, and here are the equations. I mean, the nice way to write the equations in terms of these variables, which is, I can write them in Hamiltonian form. So H's are defined by these constraints, and then I can take derivative with respect to kappa or with W, and what it describes is the variation of the conjugate variable with respect to variation of time. So this is the Garnier system, and again, yeah, this is nothing but spiration variable.
It basically introduces the times. In some sense.
Yeah, but we had introduced them before, basically.
Like you have introduced this.
So now I'm rewriting in terms of new variables. Okay, well, maybe I'll skip this slide. This was for Nikita. Maybe we can come back to because it was.
Democracy here. We don't speak. We don't address just one.
No. It's a joke because well, I can say what this is about was trying to understand a little better, but it's slightly disconnected from the. Okay, let's just skip without further comment.
Is this now for Leon?
Yeah, this is for Leon. So, now, okay, we have our moduli space of local systems. We can think of it as being the moduli space of representations of the fundamental group in PSL2C. And it is natural to define real slices in this space by the condition that the mononomy representation is conjugate to a representation in PSL2R. That is basically, I mean, I cannot think of anything else, basically. So, or maybe there is, but I wasn't creative enough. Well, as we heard basically in the first talk, I mean, this component is described by those opas which come from the uniformization, so which corresponds to the energy momentum tensor that you construct from the Liouville field, which describes the metric of Knudsen and negative curvature. So what you can do now, say, to describe now our theory on the real slice, well, you can do what Leon explained us, and then you can introduce the Liouville action. Well, there's a very intricate story about the boundary terms which Leon worked out. And from this, we can recover the H's by taking derivatives. You see, the point now is we're on the real slice, of course, the variables Z and HR, which were parameterized in the OPAS, they're no longer independent. So, a priori, of course, these are independent variables, and I have to vary the both in order to map out the space of surface group representations. Now, on the real slice, they're no longer independent, but I can take the Z's, say the parameters of complex structure as independent variables, but then on the real slice, the conjugate momenta, which were called H, they're fixed. So they're fixed definite functions, and the non-trivial plane is that's the way to compute them, by computing the Liouville action. And furthermore, you can then describe the symplectic structure or the Poisson bracket also in terms of this Liouville action by taking the second derivative of the classical Liouville action. And what it gives us is indeed the statement that the Z's and H's are canonical conjugate variables. Actually, the remark I wanted to make here is this comes from. You can also consider the space of pairs without this restriction, without going to the real slice. Then you can take H's and Z's as independent variables, and the natural symplectic structure or Poisson structure that you have is the same one, except that, of course, now you have independent variables. That is, I think, kind of important for understanding, for example, what you would get when you want to quantize space of pairs.
Wait, I just got rather mixed up. So, if we've got, I thought it was only one component of the PSL2R modular space which corresponded to Teichmüller space.
Yeah, I mean, that's the next slide. You see, there's one component. So this component.
So what was phi?
This was the component.
So what was phi? This is for the component with the maximal Euler character?
That is right. That is right. So we're restricting to this component. And okay, the story, I mean, the nice description in terms of Liouville action, a priori holds there, and I just want to present basically what replaces it for the other components.
Yeah.
Okay. Well, there's basically a general theorem of Hitchin in this classic paper of Hitchin, or can be extracted from it, that all the real slices can be represented by flat connections of this form. Where if you look at it, it is manifestly in SU11. So this is why the monodromy group of this connection is then conjugate to R. And yeah, the interesting thing happens basically here with the same beta. I mean, the same beta as before, because by gauge transformation we can set here also the diagonal components to 0, and then we're left with the 1,0 part that we've been working with before. So with beta and q as basically the variables in the holomorphic matrix differential operator. So we have the beta, and again, of course, now the plane is the main point here. Is that what Hitchin tells us is that in the general case, the number of zeros of these beta labels these different components with different Euler characteristic in modular space of flat connections, of flat SFR connections. So this is for me the nicest way to sort of introduce these different components and how to describe them, counted by the number of zeros. And okay, flatness is equivalent to this modified synchrone equation we've seen before. It is for no accident. Say more about this. And what this equation implies is that we can form a metric of negative constant curvature out of the data which appear here, namely the solution to the flatness equation, which is phi, a generalized Liouville field, and the q, which is here, the off-diagonal component. So this is just, yeah, basically the deformation by what is called harmonic Beltrami differential in the type field. Well, that's all not important. What is nice to observe and important to observe is that we have a constant negative curvature metric also for these other components, but it has conical singularities at the apparent singularities, and these are very special conical singularities, namely those with excess angle 2 pi. So we start doubly wrapping or doubly covering the Riemann surface in the vicinity of the conical singularities.
So it's not before singularity? Is it just Z2 before?
You can think of it that way.
There is a double cover?
There's a double cover. Yeah.
Is there any special reason why we don't denote q times exponential of minus 5 with some mu, some other letter, because it enters only in that combination?
Here, I could call it
everywhere, just q times exponential.
I could call it mu. Yes.
Yeah. And then it's Beltrami.
Q is holomorphic. And Q is minus 5 and all.
I mean, this
Oh,
thing,
wait.
this thing is not holomorphic.
So, wait.
Q is holomorphic.
Yeah. So it is in tight Müller theory, okay, you have quadratic differentials parametrizing cotangent directions to tight Müller space. In order to get the tangent directions, we have to multiply with the e to the 2 phi with the metric of constant negative curvature. And
so it's not
this is what makes it non-holomorphic, but it's called what is harmonic Beltrami differential. Because it's
But it still defines the...
it's tangent vector then. Yeah? So it's the way multiplying with the phi is going from cotangent to tangent. That's all. Yeah, okay, so, well, we want to do quantization. And first, let's think of the Teichmüller component. Yeah.
Just about the previous slide. Could you just state what's the what is B and what is Q? Is this one differential? What kind of?
I mean, globally, what they are.
What's the global?
What you could do is you could choose a covering where the transition functions are all in the lower diagonal, as you can always do, which is representing the bundle and the extension. This corresponds basically to setting Q to 0. It's exactly this, because then the 0,1 part is lower diagonal. And in this with respect to this representation, this is a section of a line bundle. And well, the line bundle, of course, varies. What line bundle you have varies with the number.
Is it something natural or is it very?
No, the line bundle is defined by the divisor of its zeros, basically. So you have a choice.
This one kept the card in
Okay.
What was it?
Okay, now again we want just to do a fun game, which probably what we should work more on. So we want to quantize in these variables. So we have variables z and h. We decide that the z's, which we have, well, I don't know, here as our coordinate, we decide to take the z's as our coordinates and h's as conjugate momenta, which looks natural. So then in a scalar quantization, we look of quantization in which wave states are represented by holomorphic wave functions of the z's. The representation, the representation of the basic algebra of observables is of course obtained very canonically. So we realize these guys are set by quantification operators, and these are the canonical conjugate differentiation operators. So this is a kind of coherent state in this context. Now, what do you get then by quantizing what was called T before? Well, okay, you probably remember this formula, I wrote it sufficiently often. So we get this differential operator, which is exactly what appears in the conformal Watt identities. Here's a point which needs more explanations, but basically the slogan is, which I should explain a little more, that's the quantization here basically of these coordinates produces conformal Watt identities, or in other words, the local structure of Teichmüller space, the local structure basically of the space of conformal blocks that we want to find. So this is quantization of local observables. You can also play the game to quantize global observables, which are the mononomies. Well, here I just put in a nutshell basically what Sasha has explained, or the quantization of Teichmüller space in terms of the real Fenner, Fock, control of coordinates, and so on. So I just tried to summarize what, after a certain amount of work, the picture which comes out of this way of quantizing. So you can actually, okay, first of all, classically, you can take the traces of monodromies as generators for the ring of algebraic functions on the Hitchin moduli space. Is it good theorem? Actually, I think I found a theorem which is basically saying that in your paper, but so I think it should be your thing. Or is there some details that I'm skipping here?
There are the theorems that produce your basis in the vector space.
Well, basis is stronger, of course. I'm just here for me, statement is enough, it's generating, but basis is much nicer.
Generator, I don't know.
For generators, for much older, much more.
Wait, but basis.
Okay, anyway, these are our natural non-local observables to quantize, of course. For the Teichmüller component, it's well known, and I think you've heard it, that they have a natural geometric interpretation. These are just the lengths of geodesics around those cycles. This the length in the consolidated curvature metric of geodesic. Now, okay, this Poisson algebra, by what Sasha described us, there's a nice Poisson algebra on this space, and we can quantize it. So what this defines are length operators, L sub gamma, associated with each single closed curve on the surface.
So is this what we are doing now? We're introducing different coordinates. So we had this other first one.
Yeah. So there are different coordinates, and the point is, right, it's a completely different set of coordinates, but the claim is, say, in your picture, these are going to be the deformation of these action variables, the A's, that you ultimately want to take derivatives with respect to when defining quantization condition in Young's potential. So that's what, that these guys are eigenvalues of the length operators. Okay, we can diagonalize a maximal set of commuting length operators. They are associated to non-intersecting closed curves. What this defines is the length representation for the quantum Teichmüller theory, which is a representation in terms of the eigenvalues of length operators, or in other words, functions psi of L, where L is the collection of length associated to the closed curves.
But what are the Hamiltonians?
Well, Hamiltonians for me are these the trace.
Those are Hamiltonians.
These are for me the most natural Hamiltonians. Yes. Now, second order, these are going to be second order difference operators rather than differential operators. And yeah, okay, there's to have integrable structure, you need to choose Pence decomposition, because then you find a maximum set of commuting Hamiltonians.
What is the signal there? No, you have it.
Or
Brock
again,
No,
just it should be psi.
That's
Yeah. I don't know what. Sorry, just misprint. Okay, well, let me note the basic result in this story. I'll spend some time on, which is, well, the length representation depends by definition on the choice of propensity composition. Now, the claim is different choices of propensity composition are related by unitary operators, and even better, I can represent them as integrals with respect to some kernels. So this is a way to describe the change of representation when we go from one propensity composition to another. And furthermore, there's this Liouville game. We can decompose this or construct these kernels from the kernels associated with the elementary fusion braiding estimates.
And that's an integral over L1?
That
You have
should
du
be, yeah, okay, I was pretty tired when I finished this, so it should be integral over L1.
For example, just jumping maybe a little bit ahead, some kind of S-duality transformation would also be represented by this kind of thing?
Absolutely. Yes.
And you know what would be?
The kernel is known, actually, yeah. I mean, this was, well, the time I did it, I could only know it by bootstrap, and more recently, some Hadash and collaborators have observed that the modular transformation on the torus, well, that basically the conformal blocks on the torus can be expressed explicitly in terms of the conformal blocks on 4-punctured sphere. So you can carry over whatever you know from 4-punctured sphere to the 1-punctured torus, and thereby the whole picture is complete. Okay. One of the points I like to stress is that if you bring together these two sides of the coin, namely quantization of local observables, which gives me ward identity, z's, d by dz's, and so on, and global observables, which are these length operators, if we bring together these two, we get Liouville conformal blocks. So, again, put in a nutshell, the point is, well, for the Keeler quantization, and that for me, I mean, this is one of the points we need to work more on, but for me, I would say a defining condition for a reasonable Keeler quantization is that as the mapping class group acts on the variables z, the holomorphic variables on the Teichmüller space geometrically just by basically point transformations, furthermore holomorphically, so this is holomorphic transformations, the only reasonable quantization has to be such that, well, the action on wave functions is by mapping the wave functions to its analytic continuation to the point, well, to this, to the point on the universal cover, which are mapped to by the mapping class group transformation. So it should act naturally. But on the other hand, I have a second way now to describe the mapping class group action, which is just the Pans decomposition counterpart of what Sasha described today. Namely, each Pans decomposition by an element of the mapping class group is mapped to another Pans decomposition, and I can work with the elementary flips, elementary changes of Pans decomposition backwards to go back to the original one, and thereby, by composing fusion and breakings, I'm generating this kernel. So this is the natural action of the mapping class group in the length representation. Now, well, this guy, the overlap of the eigenstate of the length operator with an eigenstate of position operator, therefore has to intertwine these two ways to describe the action. So here we have the analytic continuation of the wave function along the closed path, which describes an element of the mapping class group, and here we have the action described purely in terms of the variables L, the length variables. What this is already a kind of Riemann-Hilbert type problem. I'm describing for you the monotomies of a multi-valued holomorphic function. Well, to get a unique answer, of course, I also need to control the asymptotic behavior. And, well, there are actually, you see, the issue here is that to describe the value of the length in terms of these variables Q is highly non-trivial issue. I mean, basically it requires uniformization, it's highly transcendental. what one can do, but still it took well-known mathematicians to do it, is to describe the asymptotic behavior near degeneration limit, near the boundaries of the particular space. So if you combine some formula of Wopat with the formula of Zugraf, you're getting this formula, which is expressing the length in terms of, say, the bluing parameter in a node, the Q, and the conjugate accessory parameter. So that's a nice formula, and okay, you can quantize it, blah, 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 little discussion. And at the end of the day, you find it basically fixes the problem uniquely, fixes the asymptotics uniquely. So you have fixed monodromies, you have fixed asymptotics, and then, of course, the solution to Riemann-Hilbert type problems is unique. And, okay, if you make the calculation, you find the Liouville conformal blocks are exactly solving this problem. So this is the way to arrive at the identification between quantitative theory and Liouville theory.
So M in this formula is...
Or M, okay, yeah. Sorry,
it's not a closed path at M0.
No, M just, yeah, this is that mismatch. I mean, M is just, these are David's M's, these are the masses of external, describe the conformal dimensions of external insertions. And this is the internal stuff. I didn't want to really set up limitations here, but yeah.
Sorry. So existence test, so you know that it's unique, how do you know that it exists?
Yeah. Okay. I have to construct the solution. Yeah? So I have to construct the conformal blocks in a way which allows me to calculate monodromy. And okay, that's another talk. I'm happy to describe this, but I mean, I did this exercise. And that's really worth, because there, I think in this calculation you can sort of see the answer to one of the deepest mysteries here, which is why should there exist fusion operating transformations at all in this context where we don't have any differential equations or so. Okay, so now in the last few minutes, let me talk about the Keeler quantization of the real slices, the other slices. So we have seen that classically we were representing it in terms of O pairs of this form, where we have these extra apparent singularities. And now, yeah, it's getting a little more tricky, because we have these additional variables, and well, they're a priori unrelated to the z's we were quantizing, but on the other hand, there are these constraints which determine the Hamiltonians, so we need to quantize these constraints somehow. Well, first of all, what we can do here is, if we have d apparent singularities, it is natural, of course, to choose all of them as basic variables. In particular, if we want to reach the case of the Schrödinger system n-3, then I don't need this. Then these are by the very setup the natural basic variables.
Sorry. Yeah. I probably missed the before. What it corresponds to in the language of conformal blocks is this apparent singularities.
Yeah,
there are some.
It's the general fields, okay.
These are the
punchline away.
So now we get the question.
Because, okay, what you could have guessed it from what I've said, because these are the, if you take the semi-classical limit of the basic degenerate fields, it's exactly what creates these double wrapping, I mean, conical singularities with axis angle 2 pi. That's what they are, and so that is how we have kind of seen it already, but now basically we want just to follow more or less straightforward arguments, reproduce this, what people have guessed. Yeah, so okay, this presumably I don't have to say so much about. I mean, this is just, I return now to the description. I haven't written this, unfortunately. Well, okay, I mean here for the case n, d equals n-3, what this says is basically W's and kappas are a complete set of canonical conjugate variables. I could vary with d, then I have to supplement the subset of W's and kappas with some more variables, which I take the z, some remaining set of z's and r's. And then I have constraints.
Sorry, I can ask one more. This,
yeah.
So this turning on the times, let's see, well, the way we were thinking terms of times by other construction. This you are claiming is the turning on, putting on the degenerate field. So turning on this.
Not quite. Okay, in the gauge theory context, of course, you want to think of it in terms of surface operators. And, well, insertion of adding surface operators should be something like a Hecke modification. In fact, it's not something that you can just, well, implement on the given Hilbert space. It changes the Hilbert space. I don't know. But maybe I also misunderstood it.
So I think going from the Schrödinger equation into time-dependent operation.
Yes.
You claim it corresponds to putting the previous one, just the generate operator.
Yeah, that's right. That's right. Yeah, that's right. So
for us, turning on epsilon 2 was it?
No, that's also okay.
But I was just referring to the simple fact that you can turn on epsilon 2.
Yes, in this diagram, okay, here basically, when you start here.
I'm on that side, are you saying what I'm asking?
I'm on this side, I'm on this side. So
and
here I insert a certain number
of
of degenerate fields, so I'm getting here a certain number of apparent singularities. However, in this limit, they go away, so this is, I'm just left with the original order. Okay, that's the picture. If I would do here the other limit, they would also go away from the very beginning, because in this limit, basically, these degenerate fields are heavy sources, where here these are light insertions which decouple and factorize out of the correlation function. And that's the way, okay, I wanted to explain at some point, but the point is then, here in this limit, degenerate fields factor out to produce something like this pi psi of yk, which is nothing but the wave function of an eigenstate in Godin in terms of separated variables. But that's a different limit, and it's a different source.
Yeah. This function is precise, is it defined?
Yes. I mean, okay, I define them very indirectly here in this step. Here, a solution of this Riemann-Hilbert type problem, and the claim is the constructions of Virasoro conformal blocks do the job to produce you the more or less explicit expression for this. So they're defined, but okay. You all know it's very hard to make this very explicit. Okay, so in the general mixed case, I have W's as basic variables, and I complement this with a set of remaining Z's, and I have the corresponding conjugate variables, which are K's, which I now make differentiation operators, and a certain set of H's, which I also make differentiation operators with respect to these Z variables. That is, well, just canonical quantization coming from the Poisson structure that I have in terms of these variables. Now, I had these constraints which were crucial. They were defining me the Hamiltonian. So just as a reminder, I've put them here in explicit form again. So these are the linear equations defining the H's in terms of Laplace and W's. If you look at it, okay, here you want to put a differential operator, here you put a second order differential operator, here, okay, you want to put derivatives. That's of course what you want to do. Well, you may wonder about ordering. Let's here just put the symmetric ordering for this term here. I have to order the d by dw with respect to the w's. So getting this equation. Slight subtle. Okay, so here basically we're defining a certain number. Well, we're defining what's the counting? Well, we're defining d Hamiltonians in this way, and okay, that's maybe looks reasonably natural. However, of course, I have the remaining z's on which it depends parametrically. Still there, the complex structure. So these are the times, the deformation times, the asymptotic deformation problem. Okay, first of all, experience with, I don't know, KZ equations and geometric quantization of modular spaces indicates that when I vary the parameters which I use in the quantization, which define me the choice of polarization in the phase space, this should be described by corresponding transport of the states on the sort of bundle of Hilbert spaces.
So you want to read this as a heat kernel?
This I want to read as a heat kernel, or this is of course to be read as a kind of Knishnik-Samoshnikov type equation. But it is BPZ, of course, as you could see. Now, well, here this is basically an ansatz for the moment, but in this situation, of course, it's easy to argue that you don't have much choice, because which of the h's I chose as parameters and which as fundamental variables is, of course, rather arbitrary. This should be completely symmetric with respect to making such choices. So, but on the other hand, you see here in the quantization of what I considered as basic variables, I was just by definition putting h equals d by dz.
I think there was a big difference between the z and the w. I thought there was no monodromy in the OPR.
That is right.
And also they came in different amounts.
Yes. They come in different numbers in general, yeah. So that is, it's all right. So, that's what I'm trying to argue for. Okay, yeah, sorry. What's your question?
My question was, you were starting to talking about mixing them, and that there was no invariant distinction between them. So
there's no invariant distinction. So
there wasn't very distinction.
No, he's saying no distinction between the various z's, the one that are included in the quantization and the one that are not.
I have to split the z's into two subsets. One, I take half of this, or some number I take as phase-space variables, as independent quantities which I quantize and which I make the wave function dependent on. The rest is parameters. But which I choose as which should be completely arbitrary, and this for me basically tells I have no choice but to require that this is quantized as such. But if I do this, then I get the full set of, then my constraint equations, which were defining the Hamiltonians so far, which is just the definition of Schrödinger Hamiltonians, well, these equations now should hold with h replaced by d by dz for all values of the variable, for all the variables. And what it is of course the full set of BPZ null vector decoupling equations. Okay, so that sort of, okay, it may need more thinking about, but for me it's a very suggestive point. Yeah, let me come to the end. So basically, I hope to have conveyed a certain message. So Liouville theory is describing the quantization of real slices in the Hitchin moduli space, where we were using complex structure J, or introducing parameter epsilon. I could also hyperkila rotate away from it. The local observables gave me local structure on moduli space of Riemann surfaces, Ward identities, the differential equations. Quantization of the global observables gives me quantum loop or length operators, and furthermore mapping class group action. And if I combine the two in this Riemann-Hilbert problem, the unique answer on the relation between the two representations are Liouville conformal blocks. Okay, so the movies nowadays, they all have certain takeouts in the end, so this is now, I finished, and this is streaming up, so this is what one could want to discuss in a discussion session.
We're supposed to laugh at it, right?
Third?
We're supposed to laugh.
Yes.
Okay,
so I would want to explain more on Young's potential versus semi-classical conformal blocks, but it's kind of obvious to you. On the other hand, yeah, maybe this is a remark. Well, I don't know if you give me 2 minutes or so, I could say a word on this. Quantization of space of au pairs. So what would be the remark? Which is kind of tentative. So let's return maybe to the slice here, which I skipped. So if I think of this case of au pairs, but now without going to the real slice yet. So we're in from phi 1 of C to SL2C. Now then, first observation is the representation in terms of holomorphic differential. Well, here just count the parameters. We see that just the h's will not make up the full dimension of this space of surface group representation, the full dimension of the Hitchin moduli space. So in order to, by varying parameters of the differential equation, mapping out the space of monodromy representations I want to describe, I also have to vary the z's. I cannot help varying the complex structure as well if I want to cover basically all of the Hitchin moduli space in this holomorphic description. Okay, so how to describe? I mean, the space of O pairs would traditionally be the thing which I have when I just vary the h's and not the z's, because, well, space of O pairs, I can fix a reference O pair, then with respect to this reference O pair, space of O pairs is parametrized by the deviation to the reference O pair, which is a quadratic differential. So the space of O pairs in this sense is naturally isomorphic to the space of quadratic differentials, which is a complex space.
Projective, no?
What?
There is projective, I mean, it has...
No, I mean, okay, I fix the reference projective
or you can
projection. Say I take the one coming from uniformization, and then relative to it,
difference, okay.
The differences are quadratic different. Okay, so...
So the space of O pairs is an affine?
It's an affine
space,
yes.
Modeled out of vector space and quadratic.
That is the scientific way of saying what I did not say very good. Yes.
You say it's a torso.
Well, okay. Furthermore, if you now vary also the complex structures, what you're getting. So this is the variation of h's, and you can also vary the complex structures. Then you're getting, well, on the one hand, a subset of Hitchin moduli space, but on the other hand, what you can prove is it is canonically isomorphic to the cotangent bundle of the Teichmüller space. Well, Teichmüller space is just the underlying complex structure, and the point is that quadratic differentials are canonically giving the cotangent vectors for the Teichmüller space. Well, the point is, which I was trying to make here, is this mapping from T star T to hom pi 1 PSL to C. It is, I mean, defined by the monodromy map, of course. It is locally biholomorphic and symplectic. So this means that you can take either z's or h's. Well, both z's and h's are basically holomorphic variables with respect to the complex structure J on the Hitchin moduli space. And furthermore, it's symplectic, so the cotangent bundle symplectic structure is the omega J, the holomorphic symplectic structure on the Hitchin moduli space. So, okay, well, and of course you just get then these corresponding Poisson brackets. That is basically exactly those Poisson brackets which we had used, but now before restricting to real slice. So now it's of course the subtlety here is you can consider two slices: the real slice, or the slice of O pairs, which is kind of transversal to it, which is the one which you get by fixing z's but varying h's. And well, of course, you can now think of a kind of conjugate representation of the same quantum theory, where instead of taking the z's, the Teichmüller variables, as holomorphic variables you want to quantize. Well, sorry, one thing I should say before. Now, let's go to the real slice. But do not take these as fundamental variables, but h's that you can do. And for me, sort of, this would be what one could call more naturally, I mean, taking then wave functions as wave functions of the accessory parameters, as holomorphic functions of the accessory parameters. For me, this suggests itself as a natural quantization of space of O pairs in this sense. And maybe that's actually what you have seen. Quantum mechanically, it should be perfectly equivalent. Okay, there's going to be a non-trivial change of representation involved in going from one to another. I put it here as a suggestion that we all should think more about. So.
Questions?
First talk today on time.
It's a praise. That's not a question.
It's a statement.
It's a statement. It's not a conjecture. It's a statement.
Epsilon 2 here, okay.
These guys said it's not a conjecture. It's a statement.
the epsilon is the deviation from the
Neutral.
well, I think you can make this correspondent rather precisely.
More questions?